Swayam Prabha. Digital India. Educated India.
So far we considered the conventional Fourier transform NMR, and there what we had was one frequency axis, and when the plotted we get the intensities on the other side on the second axis. So now we enter into a new revolution which is called as multidimensional NMR, the beginning of which is of course the 2-dimensional NMR. This came into existence in the 1970s, and this actually was the main revolution for applications in structural biology. In earlier situations it was all limited to chemistry and small molecules of few atoms and tens of atoms and things like that of simple molecules. Now it was unthinkable to go into things like proteins and nucleic acids and things like that which have hundreds of protons and so many other nuclei. It was impossible to do it. To analyze this spectrum, I will show you this by an illustration here. Here is a spectrum of a protein. The spectrum of a protein, this has about 400 protons, and the proton spectrum spans as it is here from 0 to 11 ppm. Of course we have some shifted ones here, -1. This is the spectrum of lysozyme recorded on a 900 megahertz spectrometer, and you can see how much is the overlap of signals. You cannot count the number of lines here. Forget about measuring the coupling constants, forget about individual assignments to 400 different protons. How will you assign them and how will you get to the structure of them? This is quite an ambitious project to get to the structure of such a large protein, such a large molecule with so many lines. Without the assignments you can do nothing in NMR. You need to have the assignments first, and this is the water line here. We know from the chemical shift difference all of that what we have talked about is now coming into practical use. Okay. This is the water line, quite substantially reduced, and this sample is 1 millimolar in protein concentration recorded in water. Water is completely suppressed here in the 1-dimensional spectrum, and these are all the aliphatic protons, the methyls here, and these are the aromatics here, and then you have the NH protons here in this area. Okay. But you certainly cannot count them. You cannot count them and therefore you cannot assign them. Okay, then what do we do? So this is where the revolution occurred, that okay, now you try to spread this information in 2 different axes. Instead of one frequency dimension here, this is one frequency dimension, why not we generate 2 frequency dimensions and establish a correlations between the various signals in the 1-dimensional spectrum in a 2-dimensional way. And that is the motivation. That was a fantastic idea, but how to implement it? You have to generate 2 frequency axes. That is the first principle. How do we generate 2 frequency axes? And this is the idea which was put forward, and this was initially given by Jean Jenner from Belgium, and it was picked up later by Richard Ernst from Zurich, and now it really caused a huge explosion in the applications of NMR in chemistry and biology. Now the idea is following. In 2-dimensional NMR you have to generate 2 frequency axes. In the normal FT NMR you had one time domain signal, and the time domain signal after Fourier transformation you get the frequency domain spectrum which will give you the spectrum. Okay. Now you want to generate 2 frequency axes. So what we will do here is, okay, let us divide this time axis like this. Let us divide the time axis like this. So let us say we have a so called preparation period. The preparation period means we can prepare the spin system in any manner we want. It can be an equilibrium state or it can be a non-equilibrium state, whatever you want here, this is called the preparation period. Then you have a so called evolution time which we call it as T1. Then you have what is called as a mixing time We have come across this mixing time and also such concepts earlier. When you talked about the NOE, we talked about the mixing, okay. And then we have the detection time, which is called T2. This is where the actual FID is collected. This evolution time is an indirect detection period, as I will show you later. This is the detection time, actual FID is collected during this period only, okay. Now how is the experiment done? You do a series of experiments, that is you do this preparation block remains the same, and you do once with T1 value is equal to 0, then you have the mixing, you collect the FID, this is FID number 1, then you increment this T1 value, give a small value here increment, that means you separate this preparation and the mixing by certain value, that is the increment, and after that you collect the FID again, this is FID number 2. Then you continue to increment it in similar way. If the increment here is delta T1, here it will be 2 delta T1, here it will be 3 delta T1, here 4 delta T1. So you systematically increment this period and then you collect the FID every time. So second FID, third FID, fourth FID. So this is like doing the digitization. When you are collecting the FID, so we have this, the FID when it is collected, we are collecting in a digital manner, right. So we have various points here. This is what we are doing when you are collecting the FID also. So here we are actually generating this another time domain here, and this time is incremented. So just as this time is incremented, one point to another point to third point, 4, 5, 6, 7 like that. So we keep doing the first point and then the second point, the third point, fourth point, fifth point, and so on and so forth. You generate a various set of experiments, you collect so many FIDs. Therefore what you get, so that is what is indicated here, FID number 1, 2, 3, 4, 5 etc. Okay. Therefore you have so many FIDs. So now each one of them is dependent on the value of this T1. Whatever is the T1 value here, that will modulate the signal that is detected in this FID. So this FID what you are collecting will be dependent on this time, because during this period the magnetization will be precessing in the transverse plane, it will be going around in the transverse plane, okay. So therefore these will have frequency labels, during this period, and the mixing is a crucial thing which allows you to establish correlations between the spins here and the spins there, okay. Mixing establishes correlations between the evolution and the detection. Let me write that here. Mixing establishes correlations between frequencies in the T1 and T2 periods. In other words, magnetization may get transferred from one spin to another spin. What if a particular spin was precessing with a certain frequency here during this period, during this mixing it may get transferred to another spin and that will go with a different frequency. It can go with a different frequency, but whether this transfer will be complete or not complete, one does not know. It may be partially transferred. Now therefore what we have got here, we have got a time domain data which has 2 dimensions. That is what is indicated here, okay. So okay, now let me go back here. So you have a time domain data which has 2 dimensions, that is the T1 and T2. Therefore if I do a 2-dimensional Fourier transformation now, I do a 2-dimensional Fourier transformation, this is 2-dimensional Fourier transformation, I generate 2 frequency axes which we call it as nu1 and nu2. Whatever is the frequency present during the T1 period will appear along this axis, whatever is the frequency present during this period, T2 period, will appear on the T2 axis, on the nu2 axis. Therefore I have generated 2 frequency axes by doing this trick. I have given an additional T1 period, additional evolution period, during which the various spins persist with their characteristic frequencies. Now the mixing may cause transfer of magnetization from one spin to another spin. We have seen this how it happens in the various examples. We saw that in the case of inept, we saw in the case of NOE how magnetization transfer can happen depending upon what you do. It can go from one spin to another spin. All this is boxed up in this so called mixing. Okay. So therefore we can establish correlations when we transfer the magnetization, meaning we establish correlations. Okay. And the transfer may go 100% or it may go 50% or whatever. So depending upon the way the mixing is done, so you have a partial transfer or full transfer. This is what happened in the case of NOE for example. NOE, entire magnetization is not going there, part of the magnetization, part of the perturbation is getting transferred to this period to another spin, and therefore then that spin will carry the information of the past. So this is the idea. Now since we increment this T1, I generate another time variable. And the evolution carries this information of the precessions during the T1 period. Therefore various frequencies are present here and I have the labeling can be done during this period. Okay. Therefore this evolution time can be called as indirect detection period. Evolution time is also called as indirect detection, although there is no directly FID collected in the digitizer. In the digitizer of the FT-NMR spectrometer there is no direct data collection there, but we collect the data in the form of many FIDs whose evolution is modulated by the evolution during the T1 period. Therefore that modulation is dependent on this T1 period. Therefore if a Fourier transform along the T1 axis, then I get that information of modulation by the evolution here. And this is explicitly shown in this particular example here. So I have here various frequencies. Okay. This is the first FID. First FID, after I do a Fourier transformation I get a line like this. Now I have the second FID, I Fourier transform, I can the second spectrum, but now you see its intensity is not the same as this, it is slightly reduced. This is because of the attenuation here, because of the evolution here. Because of the evolution in the T1 the FID is looking different. The third one there is 0, nothing there, so therefore here also there is nothing. The fourth one it has changed sign. Why does this happen? This is because of the evolution during the T1 period. What is the situation it has reached here, the spin has reached here, that shows up in this here, that shows up in this initial point of the FID. And then you see again this will, now it has become negative, this is more negative, again it decreases in the negative because it starts going modulation, right. Positive, decrease, 0, negative, increase, negative, decrease, again go positive and so on and so forth. Okay. So therefore I get a series of spectra like this after I do a Fourier transformation along the F2. All the FIDs if I Fourier transform collect them like this. Now we look at this, look at these various points, look at these various points, find out the condition of that in each of this spectra. In the spectra I have these points A, B, C, D, E, F, G. These are all the points on the line here in the F2 dimension. This is my F2 dimension, this is the T2 period, therefore I have the F2 dimension here after the Fourier transformation. I am looking at these points here at A, B, C, D, E in this, and I see through this at this particular point what is the value here, what is the value here, and I plot that here, I plot that here. So therefore you see at the point A there is nothing, it is all 0 all over and it is all 0 here. Now we come to the point B there is a small dip, there is a small dip in the middle. Therefore if I were to Fourier transform this I get a small signal here. Now we go to point C, there is a big dip as I go take point C and I go along like this and I plot the value of the signal here, it will look like this. Now it has a time dependence, right. This is what is along this axis is T1 here, this is T1, right. So it is indicated here, this is the T1 axis. Therefore if I Fourier transform this is like an FID also, right, this is also like an FID. So if I Fourier transform this I get a signal. So go to point D, greater dip, greater intensity, go to E, dip has decreased, smaller intensity, go to F, again it has decreased further, small intensity, go to G here, then no signal, 0 intensity. Therefore, you see here, as a result of this kind of an experiment, I have got the frequencies along both the F1 and the F2 axis. Okay. So, this is what is the principle of 2-dimensional NMR, which is summarily described here. So, you have the 2-dimensional NMR, you have S T1 T2, time domain signal has 2 time components T1 and T2. You have to do a 2-dimensional Fourier transformation and generate a 2 frequency axis F1 and F2. Okay. So, and these are independent Fourier transformations, you can do either one, whichever order you want to do, it does not matter. Okay. Alright. So, now that was the principle of 2-dimensional. I give certain examples here, what all things, whereas various kinds of 2D experiments. We will not go into the theory of these calculations, we are going to use these ideas and describe some experiments, how these experiments, what are the pulse sequences here and what is the information that comes in these experiments. One of the very early experiments that was done was 2D J-resolved spectroscopy. Okay. The J-resolved spectroscopy is done in this following manner. Okay. So, you have first a 90-degree pulse, 90-degree pulse. Now, the evolution period is from here to here, evolution period is from here to here. Okay. But we have put a 180-degree pulse in the middle itself, that does not matter, we can do that, but the time is incremented here. Now, what is the consequence of this? The consequence is from here to here, this is an incrementable time, we are going to collect various FIDs with incremented t values, right. So, as a function of T2. Now, from here to here it is the same as the spin echo, okay. This point is the spin echo. So, this sequence 90 180 tau, 90 tau 180 tau, okay, that is the spin echo. So, during the spin echo what happens? That is indicated here. During the spin echo chemical shifts are refocused, right. In the spin echo chemical shifts are refocused, but the J remains, the J information remains, the coupling constants are not refocused in the spin echo. This is what we saw earlier and also in the inept experiment we explained that how the J information is not refocused in the spin echo period and therefore the J information is present here. And this is my evolution. Therefore, what is the information present during the evolution period? The T1 period, that is a J. J information, so frequencies correspond which describe the J are present. Okay. So, it is like sitting in the center of the line and looking at the 2 transitions A1 and A2 transitions, how they are precessing, You sit at the center of one line, let A1 and A2 are the 2 transitions of the A spin, you are sitting in the center because your chemical shifts are refocused. The chemical shift information is not present here anymore. So, during this T1 increment what is changing? The 2 transitions A1 and A2 they keep moving. Let me write that here. So, they keep moving during the T1 period, they keep evolving, okay. They are in the center, okay. This happens for every spin, because the chemical shift information is removed, what it is at 0 frequency, chemical shift does not have information at all. So, only the J values are present during this period, okay. That is the effect of the spin echo. I repeat here again, the chemical shifts are refocused, no matter what the chemical shifts are, that is completely eliminated at the time of the echo until this period, which means it is like sitting at the center of the multiplet for every nucleus, because the chemical shift information is not present. It is like sitting at the center of every multiplet for in your spectrum. Therefore, we consider only this kind of, I take a 2 single doublet, the 2 transitions keep evolving as a function of T1, okay. Therefore, what is getting modulated as a result here? So, what is the modulation that is happening? J evolution is contributing to the modulation. So, therefore, J evolution Therefore, if I were to Fourier transform along the T1 period, what I am supposed to get? I should get the J information. J is the frequency. I should get that frequency, right. The angle modulation creates a different phases and the FIDs will be modulated by that evolution. Therefore, if I Fourier transform along this, I should be getting the J information. What happens here in the T2 period? T2 period I have done nothing. I am collecting the data as if it is a normal one dimensional spectrum. I collect the data as if it is a normal one dimensional spectrum. One dimensional spectrum has both chemical shift and the coupling constant. Therefore, I have the J plus delta, both informations are present here during the detection period. So, during the spin echo, during the T1 period I only have J, and during the detection period I have both J plus delta. Therefore, this experiment is called as J resolved spectroscopy. Okay. How does this look? So, you see this is explained here, this is called as 2D separation here. Now, this is the consider this sort of a system here, you have a one doublet and a triplet there. Now, along the F2 period I have both the J and the delta. Now, this axis is delta plus J, this axis is delta plus J and this axis is only J. Okay. So, delta plus J and J, what it will give me? Along this frequency axis I will have the J information, this axis I have the chemical shift information. Therefore, for a doublet I will have these two lines oriented at a certain degree, at a 45 degree here. They will be oriented at 45 degrees with a central line, because there is a J by 2 and J by 2 both places, right. So, this is the center and this is the doublet, right. So, this is J by 2 here and this is also J by 2, the doublet. So, the doublet, this is J, this total is J. From the center to the end it is J by 2. Therefore, one of them goes up here and this is, and then the total from here to here is J. That is what is called the J separation. Along one axis I have the J information, along the other axis I have both J plus delta. Okay. So, therefore, when I consider in the 2 dimensional spectrum I will have these the peaks appearing at an angle of 45 degrees, because you have J by 2 and J by 2 means it is an isosceles triangle. Isosceles triangle means it is a 45 degree angle. Therefore, I will have here the doublet appearing like this and the triplet will also appear like this, and we have the, in the triplet of course we will have the one line at the center. Okay. Therefore, triplet appears. Now, what we do? We do not want this angle, we do not want this angle. What we do is, during the processing process we will move this fellow to this center, we will move this fellow here, we will move this fellow to the left, move this fellow to the right, and similarly we move this fellow to the left, move this fellow to the right, so that we bring all of these on the same line and we bring these two in the same line. That is what is done here. This is done by moving one of them this way, other one this way, and here this also again moved this way and moved this way. So, let me indicate that here. Okay, when you move this, so they will all come on the same line. So, as a result I will have this spectrum. Okay. Now, you see on the J, on the, this is the F1 axis, or it is also called as the J axis. Now, I have simply looking at the separations here, I can measure the coupling constant, and if I take the projection of this I will have only one line. If I take the projection here, I will have only one line, correct, which means I have decoupled them, which I have decoupled the two spins. What was a doublet here now appears as a single line, what was a triplet here will also appear as a single line. So, this is a homonuclear broadband decoupling. So, this amounts to broadband decoupling. the coupling information is removed. Therefore, your lines will get simplified, right. So, your spectrum will get simplified. So, you will have multiplicity is removed. So, you will have one line per spin. Therefore, you have a very higher resolution in this kind of a spectrum, but you have not lost the coupling information though. The coupling information is retained along the other dimension. So, therefore, this experiment is called as 2D separation or J delta separation. In a 2-dimensional experiment, we have achieved this sort of a result. Okay. So, now we see here it is a more complex system there. We have many spins and I have just shown the spectrum here for your information, and I do not even know what molecule it is, but nevertheless it does not matter. You have here a doublet, you have a triplet, then you have a doublet of a doublet here, then you have again possibly a triplet here, but with a smaller coupling constant. So, here you have a triplet, again a single line, and then you have a doublet of a doublet, again doublet of a doublet. So, you can see all the coupling information can be obtained, and look at the range here. The range is minus 10 hertz to plus 10 hertz. So, 20 hertz, this is about I mean you do not have any fine splitting which is more than that. So, you will have here the separation which is like about 10 hertz, you are able to measure this 10 hertz separation, and this will be 20 hertz here and so on and so forth. The coupling information is present, and if you take the projection down here, each one of them will give a single line, all of them will give a single line. So, this will be a single line, this will be a single line here, a single line there, a single line there, again a single line there, a single line there and a single line there. If you took this projection onto this axis, you will have only one line. So, there is a completely chemical shift information is on one axis and the coupling information is on the other axis. So, therefore, this is an extremely useful technique for handling large molecules, because you have achieved a good resolution enhancement along the F2 dimension by decoupling, but you retain the coupling information along the F1 axis, therefore you can extend the coupling constant also, you have not lost it. So, it is like sitting on the line, the spectrum, and rotating it by 90 degree like this. So, you have the spectrum like this, sit in the center and rotate it by 90 degree. Therefore, you have a much better resolution in your final spectrum. Okay. Well, so this is a little bit more modified technique of refocused inept, and as a consequence we already discussed the refocused inept earlier, and this experiment is now converted into a 2-dimensional J-inept experiment. In this case, what we have seen this earlier, this experiment we discussed earlier, the refocused inept. Okay. So, basically, and we do a decoupling, of course we can get this. Now, what we do is, instead of this period being a constant time period, what we do is we make it as an evolution time. We make as an evolution time. When we do that, you generate the second frequency axis here. When you do the second frequency axis, you are able to produce the frequency axis along the F1 dimension, Fourier transformation, you get such a beautiful clean spectrum and 2D J-inept. Identification of carbon types, by looking at this you can identify what kind of a carbon it is. Along this axis you have the carbon frequencies, and along this axis you have the J's. So, the single doublet, therefore this is the CH group and this is the CH2. CH2 you have a much larger separation here in this, then another CH2, then you have the CH here, then you have the CH3, which we saw earlier, we saw in the case of 1-dimensional spectrum how these ones will appear. Okay. So, you can identify the carbon types by doing such a kind of an experiment. Okay. So, I think we can stop here. We will go into this next kind of 2-dimensional experiments in the next class.